Now it's the last chapter of this series of lectures. I want to list the applications that I stated at the beginning. So first application, I will also add some applications. First application is Malchev and Selberg properties. So to state these properties, these are properties which are usually satisfied and proven by Malchev and Selberg concerning finitely generated linear groups. Okay, so I say that gamma, a group, is finitely generated. This I already used. If there is a finite set S in gamma that generates gamma as a group. Okay, and usually I write like S is gamma is generated by S. This is like F1 up to Fs, where the Fi are the generators, are the elements of S. Okay, and second definition, so this was for finitely generated. Gamma is residually finite if, as soon as you take an element in gamma which is not the identity, the neutral element, so let's say neutral element, there is a finite group F, and there is a homomorphism from gamma to this finite group, such that the image of your element is not the neutral element in F. Okay, so you can, let me say it again. You have a group gamma, and you look at the elements of gamma which are not the neutral element. Okay. Then to decide whether such an element is or is not the neutral element, you just have to look at all the finite quotients of gamma. Okay. Oh, thank you, Alexis. Yeah. An element is a neutral element if and only if it's a neutral element in all finite quotients of gamma. So in fancy words, gamma embeds in its profinite completion. And gamma is virtually torsion-free if there is a finite index subgroup in gamma which is torsion-free. Okay, so up to finite index, I can kill all possible torsion elements. So that's a new definition. So it's virtually something if the property is satisfied by a finite index subgroup of my group. And so the theorem, so this is due to Malchev for the first property when the group is linear, to Selberg for the second property when the group is linear, and to Bass and Lubotsky in this context. So if X is an algebraic variety, let's say I will state it over C. There are versions over other fields. Because here, today, I'm using characteristic 0. Then any finitely generated subgroup gamma of the group of automorphisms of X is both residually finite and virtually torsion-free. Okay, so this residually finite property is the Malchev property. This one is the Selberg property. Okay. Yes, of course. Yes. I mean, the example I have in mind is X is the affine space, and I will prove it for the affine space. Okay, so step one. We introduce, let's say, C. Okay, so it's the set of coefficients. So I recall what I did yesterday, except that the set of coefficients, I called it S yesterday. Set of coefficients of the formulas defining a finite set of generators F1 up to Fs in your group gamma. Okay, so you write, so here I'm using that X is the affine space, so you write the element of gamma in affine coordinates. So you choose a finite set of generators. So you write explicit polynomial formulas for the Fi, and you list all the coefficients that you see. Then there exists a prime P and an embedding of Q of C into QP as such that iota of C is contained in ZP. Okay. I don't put 0 in my, I mean, like this it is correct. So I started with a subgroup of the group of automorphisms of the affine space over the complex number. Now I get a group, let's say, gamma, you apply iota to all coefficients, which is now in the group of automorphisms of the affine space, but with coefficients in ZP. Okay? And since I'm applying a field embedding, I mean, being the identity in my group gamma or being the identity in gamma after I apply iota, it's the same thing. So here it is. And now I simply use the following fact. So here I don't really need the group of diffeomorphisms that I introduced during the previous lectures. But since I explained it in that case, I will do it here. Okay. And this group contains a group D that I introduced yesterday. D is a finite index subgroup. Why do I need this? I don't need this. at this stage, I don't need this group D. So I'm just saying now that this group acts by permutations on the finite set of polydisks of radius p to the minus c in z p to the m for every c in n. Okay, equivalently, after reduction mod p to the c, it acts on the finite set of points with coordinates in z to the p to the c. Okay. Okay, so I get a sequence of homomorphism from this group to the group of permutation of this finite set, sequence parameterized by C. Okay. So I get a lot of homomorphism to finite groups. A group of bijections of AM Z mod P to the C. Let's say it's homomorphism theta C. Okay. So now let me prove that it is residually finite. You take an element here in your group gamma, let's say an element G, and assume that G is not the neutral element, so it's not the identity as an automorphism. Okay. Then it's not the identity as a diffeomorphism. Because it's not the identity, there is a point which is mapped to another point. You compute the distance between these 2 points, okay. The p-adic distance. It's p to the minus c for some c. And now apply this homomorphism for c prime, which is larger than c. And you see that the point modulo p to the c prime is not fixed. That's it. Okay, so this proves residual finiteness. Okay, now I will need my subgroup D for step 3. Step 3, I want to prove that it's virtually torsion-free. So come back to this inclusion. So gamma, after I apply iota, is contained in this group, which embeds into this group. And here I have a subgroup D. Okay. Subgroup D was the subgroup of elements in this group of diffeomorphism acting trivially modulo P. Okay. And I explained yesterday that an element in this group, which is torsion, has to be the identity. And this group is finite index. So I just have to take the intersection of iota gamma with D. This is finite index in D and torsion in gamma and torsion free. So this proves the result. Okay. Okay, so for instance, if you have a group which is infinite and torsion and simple, you cannot embed it in the group of automorphism of such an algebraic variety. Okay. Okay, so for instance, there is this famous Grigor-Schuk group. You cannot embed the Grigor-Schuk group in. Yeah, it's a corollary. Okay. So there are, with this very basic fact, there are many groups finitely generated that you cannot embed in the group of automorphisms of an algebraic variety. Okay? So here I made the proof for the group of automorphisms of the affine space. If you want to prove it for an algebraic variety X, then you just have to add things in your set of coefficients. You add coefficients of equations defining X. Okay. And then when you talk about the formulas defining an automorphism, you have to choose such formulas. You know, it's not unique. Okay. So second property. Okay, so let me remind you, what do I want? What is the statement? So a theorem. Okay, take, so let X be an algebraic variety over C. Let F be an automorphism of X. W in X an algebraic subvariety. And Z in X of C a starting point. And then you look at the times n in Z such that Fn of Z is contained in W. Okay. So this is what I denote by the visiting times starting from Z in W under the dynamics of F. Okay, and the theorem is this is a finite union of arithmetic progressions. Okay, so that's the statement we want to prove. Let's say, again, I will prove it for X, the affine space. And step one is the same step as in the previous proof with C, which is, you put in C, you put the coefficients of formulas defining your automorphism F. You put the coordinates of Z. And you choose equations of W. So let me write it here. Okay, so this is defined by a finite set of equations, and so you put the coefficients. Of this equation Pj. So you put all the data involved in the equations and formulas defining your problem. Okay? And then you make this, you choose such an embedding of the field Q of C in Qp such that iota of C is contained in Zp. Okay. And then, if I mean, this set of times n with this property is unchanged if I apply iota to the formulas. Yeah. So this is exactly the same set. So it's n integers n in Z such that f, after I apply iota, iterated n times of iota of Z, is in W after I apply iota. Okay. Okay, step 2. What is step 2? Okay. Step 2 is a little trick. So I want to apply this p-adic method. So I want to put f in a flow and use p-adic analysis. To put f in a flow, I need this assumption that f is the identity modulo p. So I will choose here p at least 3, so that you know, I have this 1 over p minus 1 in all my formulas. So, and the trick I explained yesterday is what you can do is you can renormalize. I mean, you can iterate f to be sure that f is the identity mod p, and then you can iterate again to be sure that the differential is the identity, and then you can renormalize by multiplication by p. Okay, but when you conjugate by multiplication by p, you move the point z by multiplication by p or 1 over p. You don't want this z to be mapped outside of the polydisk when you divide z by p. So first, what I do is I conjugate everything by translation by z to put z at the origin. Okay. So these are like preliminaries. Okay. So you do that. So now, after you do that, you replace z by the origin 0, 0, 0. You replace f by f of x plus z minus z. You replace w by something, etc. Okay? So you do it, and now everything is defined over Zp again, and we can assume that Z is the origin. Okay? Okay. Now, consider an integer L at least 1 such that FL of the origin is equal to the origin mod p square, and the differential of f at the origin is the identity mod p, and set g is 1 over p fl of px. Okay? This I explained yesterday. You know, f is contained. Okay. This I didn't say because it's exactly as in the previous proof. F is an automorphism of the affine space. It becomes an automorphism of the affine space defined over Zp. So I can consider it as an analytic diffeomorphism, and there is some iterate in this group D. Okay? Or if you prefer, you look at the action modulo p square, it's an action on a finite set. So there is an iterate that fixes the origin, And then the differential at the origin becomes an element in GLM of Fp, which is a finite group. So if I take a further iterate, it's the identity. Okay. Then I do this trick, and now my G is the identity mod P, in the sense that all coefficients except the one corresponding to the identity are less than 1 strictly in absolute value. Okay, when you reduce the coefficients mod P, it's like this. So I know that there exists a flow by, let's say, from Zp times Zp to the m to Zp to the m. Okay. Tx maps to phi index T of x, such that G is phi at time 1. Okay? So these are the preliminaries. You know, I'm using two little tricks, make a translation, then iterate and zoom by multiplication by p to do that. Okay, so note that 0 is fixed by x goes to px. Okay, so when I do this conjugacy, the point I'm interested in is again the origin. This has not changed. And what was the second thing I wanted to say? Now, when I iterate G n times, because it's just conjugacy by multiplication by p, it's the same as the conjugacy of f iterated nl times by multiplication by p. Okay? So now I will look at what? I will look at the visiting times of the G orbit of the origin in what? In 1 over p w. Okay? G to the n of the origin is contained in this, means f to the nl of the origin is contained in w. I put 1 over p here to cancel this 1 over p. Okay? And the equations of 1 over p w are what? Are this function p index j, which I multiply by 1 over p after I apply my embedding iota. You're right. You're right. I made a mistake here. Ej of px, right? Okay. Okay. So if I control or understand the visiting times for this new dynamical system generated by G, I will not have all possible visiting times. I will just have the visiting times with respect to f, which are divided by L, which are a multiple of L. Okay, so the trick is the following. I will do it for this one, and then for 1 over p f of w, etc., up to 1 over p f to the L minus 1 w. And then the equations, I mean, it's like pj pf minus 1, I mean, minus jx. Okay, so instead of looking at the visiting times in just 1 over pw, I will have to do it for 1 over pw, 1 over pfw, etc. Okay, and then I will have all possible visiting times for the orbit of the origin under the dynamics of f, because I will have all possible integers of type nl plus j for some j between 0 and l minus 1. Okay? So let me explain what happens for 1 over pw. So these were just preliminaries. Now comes the main ingredient. G iterated n times of the origin is in this 1 over pw if and only if the equations are satisfied for this point. Okay. So if and only if pi index p of 0 equals 0 with t equal n. Okay, so I'm interested in this type of equations for j. What was my notation? Oh, I have two L's which are not the same. Okay, let's say the number of equations is R and the number of iterates is L. Okay, so I have to study this type of equations when now the variable, in fact, I'm interested in the case where the variable is just an integer, but I can look at this equation when the variable now is a p-adic number in ZP. And what is it? I mean, I fix j. This is a p-adic analytic function. I mean, a p-adic analytic curve parameterized by t in the affine space, okay, which I compose with a polynomial function. So I compose it with an analytic function. So the composition is p-adic analytic. You know, when you compose analytic things, it's okay. Okay, so the set of zeros, or the number of solutions, is either finite, in case I have only finitely many possibilities for n, or it's infinite, and then it's equal to everything, to ZP, by the isolated zero principle. So the set of solutions is finite or equal to ZP. Okay. In other words, when I come back to this property, the set of times for which the orbit visits 1 over pw is either finite, and I'm good, okay? A finite set is a finite union of arithmetic progressions, or it's infinite, and then it's satisfied, in fact, for all times n. Okay. Is it clear? So the visiting times for G starting at the origin in 1 over pw is equal to a finite set or Z. And now when I come back to F, F is related to G by the fact that G is F to the n up to conjugacy. So you get that the visiting times with respect to the dynamics of Fn for the point Z in W is either finite or Z. Okay. When you go back, sorry, it's not N, it's L. When you go back to the visiting times with respect to F, you change this Z in L times Z. Okay. So this makes finite or L times Z. So this is for W, visiting times in W with respect to the dynamics of F. Okay. Here it's for the dynamics of FL, here it's the dynamics of F. And now you have to do it for all these subvarieties, and then you get finite sets plus arithmetic progressions of type L, Z plus S for some S between 0 and L minus 1. Okay, that's the conclusion. Okay, so I proved the theorem, and moreover, I gave an upper bound for the steps of my arithmetic progressions. This upper bound is given by the L I need to apply this Bell-Punnon theorem. Okay? So when I stated at the very beginning that it was like an open question to be algorithmic or explicit on the type of arithmetic progressions you are looking at, in fact, the steps, it's okay. What is difficult is to decide whether there is at least one time for which the orbit visits W. Okay, so now let me jump to the last statement I gave. Or maybe I... Okay, so let me add some remarks. Now, the following two facts, in particular the fact that if F is an automorphism of the affine space of dimension M over Z, then it's periodic points Z with integral coordinates have period at most, so what is it? 27 to the M. Okay, this is now an exercise. Okay. Everything, so this, you know, this is what I said at the very beginning. So if you have an automorphism of the affine space defined by integral formulas such that all the integer points have periodic orbits, then in fact the transformation is itself finite order. To prove it, you just have to prove that there is a uniform bound on the length of on the periods of the points, you know, the length of the orbits. Here is a uniform bound. How do you obtain it? Since I started with something in Z, you know, the first preliminary steps, the coefficients, blah, 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 are just integers. So you just want to embed Q in some QP, for which you can do this Bell-Punnet thing. You choose P equals 3. That's the first thing. And then you just have to control the size, the index of this group D, or if you prefer, the order of M by M matrices with integer coefficients modulo P, so modulo 3. And this is where comes this 27 to the M. Okay, so now last statement. How much time do I have? 15 minutes. So let me do some kind of introduction to this last thing. So start with your favorite Lie group. Okay. Okay, so you can. So I will write, let's say, I mean, this is also interesting for solvable or nilpotent groups, but say simple or almost simple Lie group. Okay, so you can take SL R with real coefficients or SO PQ with real coefficients, etc. Okay. And then you do the following thing. You do the representation theory of G in finite dimensional vector spaces. Okay. So you know, you look at, for instance, for SLR or SOPQ, I mean, for these simple Lie groups, you have this theory of highest weights and so on, and decomposition in irreducible representation. So this you understand. Okay, so now you add a new column, and this is what, now you take the same Lie group, and try to do the representation theory of G into diff of M, where M is a compact manifold. Okay. So, and then you try to compare the two theories. Okay. Okay, so of course, on the left, this is a well-known subject with a lot of results. On the right, we don't know much. Okay. But what we know, for instance, is examples on the left give us an example on the right. For instance, SL R of R acts on R to the R, and then this gives you an action of PSLR on the projective space of dimension R minus 1. Okay. And this is the smallest dimension that you get for an action of this group on a manifold coming from what you know from linear representation and homogeneous varieties. And the question, for instance, is, can you say that the complexity is at least that one? In the sense, can you say that there is no action of this group on a manifold M of dimension less than that? Okay. And the answer is yes. It's a Lie theory. Okay, so the theory of Lie groups acting on manifolds tells you, I can prove it if you want, that this one is easy, tells you that the group PSLR does not act almost faithfully on a compact manifold of dimension strictly less than R minus 1. And what is the Zimmer program? You try to do the same thing for groups which are not Lie groups, but for which you understand correctly the representation theory, and try to compare what happens for linear representations to what happens for actions by diffeomorphisms on compact manifolds. And a typical example is, and this is what Zimmer suggested, is now you replace G by gamma, a lattice in your Lie group. So a lattice in your favorite simple Lie group. Okay, a lattice is just a discrete subgroup such that the quotient has finite Haar measure. Okay, G mod gamma has finite Haar measure. So here you can take a SLR of Z. Okay, then what happens, in fact, if R is at least 3 in this example, or mean of PQ is at least 2 in this example? In fact, the right condition is that the real rank of the Lie group is at least 2. You have Margulis rigidity and superrigidity theorems, which basically tell you that the theory of linear representations of such a lattice is determined by the representation theory of G. So it's basically the same. So there are some little issues, but basically up to finite indices, every unbounded linear representation is induced by a linear representation of G. And then you can ask the same question now when you replace G by gamma. So you want to understand actions by diffeomorphisms on compact manifolds of lattices in Lie group. And you want to know whether these rigidity results of Margulis have some kind of counterpart in the setting of differentiable actions on compact manifolds. Yeah. And then you can ask the same problem for groups of birational transformations. Okay, so this problem has been solved recently by Brown, Fischer, and Hurtado. Okay. I mean, if you want an introduction to that, I wrote a Bourbaki seminar on this subject. And now, so what I'm interested in is something which is a little bit different, but similar in spirit, is the same type of questions for groups of birational transformations. And as I said in the first talk, what we proved with Juni Xie is the following fact. So let G be a simple or almost simple real Lie group, and of rank R. Okay, so now let gamma be lattice. So I let some space here, okay? So if you take notes, do the same. And gamma be a lattice in G. If gamma embeds into the group of birational transformations of X, where X is a complex projective variety, then the dimension of X is at least the rank of the group. Okay, so this is not exactly what we prove. So let me add a comment. This is what we want to prove. Unfortunately, we prove it only for what is called non-uniform lattices, which means that we have a lattice, so G mod gamma has finite R measure, or if you prefer, there is a set, a measurable set omega in G, such that when you translate omega by all elements of gamma, you cover G. And the R measure in G of omega is finite. Okay, so that's definition of lattice. What we are asking when I say non-uniform is the fact that G mod gamma is not compact. So that's the meaning of being non-uniform. Okay, so for instance, if you take G to be SL R plus 1, the index is R plus 1 because I want the rank to be R, which means here that the diagonal subgroup must have dimension R, so there is R plus 1 coefficients because determinant is 1. Then you can take gamma to be this group, SL R plus 1 of Z, and the theorem applies. But you can also replace gamma by any finite index subgroup in this group. Okay, and there are other examples of non-uniform lattices. The result I stated during the first lecture is a little bit different because in this specific case, when gamma is a finite index subgroup in this lattice, in case of equality, you can say more. Okay, you can say that in case of equality, X in fact is birationally equivalent to the projective space, and the action is conjugate to a linear projective action. Okay, 3 minutes to explain some of the ideas. Oh, that's true, that's true. So 8 minutes, which does not solve the problem of explaining the proof, you know. But oh, no, I can always assume X smooth. Because if X is singular, I replace by a smooth model and I conjugate by that, I am still in the group of birational transformations. Okay. So I don't need to assume smooth. Okay. But I have to assume characteristic 0. Okay. So yes, this is a good remark. Of course, what we conjecture is that the same result is true for uniform lattices, so co-compact lattices. And we have no counterexample if you work with varieties which are defined over a field of positive characteristic. So it might be true also in positive characteristic. What else? Also, you know, I'm talking about Lie groups and lattices in Lie groups, so I'm working, if you prefer, with algebraic groups which are defined over R or C, and their lattices or irreducible lattices. I could also look at p-adic Lie groups and their lattices, or more generally, algebraic groups over non-Archimedean fields and their lattices. This I didn't study, so I'm not sure what I should conjecture. In the case, for instance, the field is a function field, a function field in one variable over a finite field that you complete. This I didn't study, but maybe there are results like that for this type of lattices. Okay, so let me explain the proof. Case one, I will do it not for birational transformations, but for automorphisms. So assume gamma is in SLR plus 1 Z of finite index, and gamma embeds into the group of automorphisms of a variety, not projective, okay? And for simplicity, of the affine space. Okay? No, it's already hard for this group. Okay? What I want to show is M is at least R. Okay? In that case, in fact, I can show M is at least R plus 1. Okay? It's a little better than what I wrote. So the goal is here, it's this one. Okay, so first result, such a lattice and all its finite index subgroups are finitely generated. I mean, for this lattice, it's easy. You generate it by elementary matrices. Okay, so I can use again and again the same first step. I can assume everything is defined over ZP for some large prime P. Okay, so in fact, now I can replace this by the group of p-adic analytic diffeomorphism of the polydisk ZP to Z. Okay, and since I can replace gamma by a finite index subgroup, I can also assume that gamma is contained, its image is contained in D, my nice subgroup of the group of diffeomorphisms. The one for which every element in D is in fact time 1 of a flow. Okay, so this is, I'm just writing in 3 lines all these preliminaries that I explained in the previous proofs. Okay, so now I know that for every F in gamma, there exists a flow associated to F such that F is this flow at time 1. Okay, so now I have a group. I don't have just one transformation. Okay, so for each element I have a flow. So I put a F here, an index to remember that it's associated to F. Okay, and the fact is that these flows are compatible, at least on a finite subgroup, finite index subgroup of gamma. So if I replace gamma by a finite index subgroup, these flows are compatible in the following sense. So let me explain. Okay, let me read again what I mean by this. I start when I have one element by an action of Z. Z is just the set of iterates of F. Okay? So if I look at it for just one automorphism, I have an action of this discrete group Z, and here I end up with an action of Zp for the addition. So now I have an action, in fact, of gamma. And gamma is finite index in SLR plus 1 of Z. And when I say that these flows are compatible in the following sense, in the set that they define, in fact, an action of a subgroup, a closed p-adic analytic subgroup let me write it like that. It's a congruent subgroup. Of SLR plus 1 of Zp. That is, I will explain it more precisely. G will be subgroup G. G will be matrices M in SLR plus 1 of Zp, such that G minus the identity, G in SL, G minus the identity is less than P minus N for some large N. Okay, so this is the crucial fact. Okay. So you started with a discrete group, SLR plus 1 of Z, or a finite index subgroup of it. You end up with an action of this p-adic analytic Lie group, or in fact an open subgroup in it, okay, on Zp to the M by diffeomorphisms. Okay, so you get something like that, G times Zp to the M, and an action onto Zp to the M, which is p-adic analytic. Yeah. You know, it's like if I were using real coefficients, it's like starting from SLR plus 1Z, ending with SLR plus 1 of R. And I said that Lie theory tells you that you cannot act in small dimension. And then you just copy Lie theory, but in the p-adic settings, and you get the result you want. You get, so M, it is at least R plus 1 in this example. Okay? So this is what you get. So this is, somehow it's simple. Where did I cheat? It's when I just say, oh, the crucial fact is, you have to prove this fact. Yeah. How do you prove this fact? You know, I explained that you have this group of p-adic analytic diffeomorphisms, and then you have all these flows, and you want to show that they are compatible to define such an action. Okay. So there are relations in this group. You want to show that they are satisfied by these flows. Okay, so here you have, abstractly, you have the group of diffeomorphisms, of analytic diffeomorphisms, but more concretely, if you reduce modulo a large power of P, you have an action on a finite set, which are the points with coordinate in Z mod P to the C Z. And you can take all this in families. I mean, for all possible reduction mod P to a large power. Okay, so you have reduction to finite groups. Okay. And these finite groups, you understand them well. And this is related to finite quotients of your group gamma, of course. So your problem is to understand whether you understand these finite quotients. But the finite quotients of SLR plus 1Z or of gamma, because my lattice is non-uniform, I know that they satisfy the congruent subgroup property. So I know that I understand the finite quotients of my lattice. Here for SLR plus 1Z, this is not so difficult. Okay. Every finite subgroup up to some small errors at the beginning, every finite subgroup is a subgroup of SL, is a subgroup which is obtained by writing an equation that the matrices are equal to the identity modulo some integer up to some well-defined index. So let me say it again. To construct finite index subgroup of this group, you can reduce modulo n for some n, take a finite subgroup of that, and take the pre-images. Okay? And this gives you the finite index subgroup. And because of the P here, which is everywhere, the subgroups which are involved are the finite index subgroup, which are congruent subgroup when you look at congruences modulo power of P. And this is basically the pro-P completion of SLR plus 1. Then use this, you use it. Okay, I stop because I'm...
Do we have any short questions?
Sorry.
Yeah, in the proof of this, the last theorem, I couldn't see why do we need to assume that this Lie group is simple. So can you...
To assume what?
Why we need to assume the simplicity of this Lie group. So can you extend the result to any compact Lie group? Or
Any what?
Any compact Lie group.
Compact?
Compact, yeah.
Oh, for a lattice in a compact Lie group is a finite group.
Oh, yeah, sure.
Okay, so...
Yeah. So for example,
so your question becomes, given a finite group, what can I say on the smallest dimension of a variety that contains this finite group in your group of birational transformations?
And,
okay? You say, if you want this, I mean, this is also interesting, of course, for finite group instead of finitely generated groups. Yes. What is the smallest, given a finite group, what is the smallest dimension of a variety such that your finite group embeds in the group of birational transformations of your variety? Okay, so this is really, I mean, it's interesting, but it's also important. Okay. I never remember the definition of this notion, but the name of this notion, but it's very important. But this type of techniques, you see, I replace everywhere all my elements by some power such that they are in a flow. Yeah. Okay, so everything I do is up to taking finite index quotients. So it's completely useless for finite groups. Okay, I'm cheating a little bit. I mean, some of these ideas can be used also for finite groups, but are not very efficient.
Thank you.
Another short question,
yeah? Yes. It's super simple.
So, okay.
Okay. Take such a Lie group, let's say G. Assume G acts on a compact manifold M. Okay. Take take the maximal compact subgroup of this group. So here you see I started with this Lie group. You take SOR. Put a Riemannian metric on M and average. So your group now, your maximal compact group, is acting on M by isometries with respect to a Riemannian metric. Okay. Now look at the stabilizer of a point, any point. Take a point and look at the stabilizer of the point in your maximal compact subgroup. Okay. The codimension of the stabilizer is at most a dimension of M. Right? Okay. Is it clear? Oh, it's clear, no? So here I have the maximal compact subgroup acting on M. I pick a point X, and I look at, let's say, K index X in K, the stabilizer of X. Yes, okay? Then the orbit of X is K divided by Kx. the dimension of that is less than the dimension of M. So the codimension of Kx is less than the dimension of M. Okay. So now there are two steps. I want to control the dimension. I mean, there is one main step. I want to control the dimension of this. How do I control the dimension of this? So it's a compact group fixing a point X and preserving a Riemannian metric. So I have a map to GL of the tangent space of M at X. This has dimension, the dimension of M, and you preserve a Riemannian metric. So you are in the orthogonal group with respect to this Riemannian metric. Okay? And so the dimension of this you can bound also. Dimension of this is bounded by something that depends on M. Dimension of the quotient is bounded by the same dimension. Okay, so all I have to show is to show that this is injective. And why is it injective? Because if you have an isometry for a Riemannian metric, which is which fixes the point and the differential is the identity, locally it's the identity, just because the exponential map gives you a diffeomorphism that conjugates the action on the tangent space to the action locally. Okay, so the set of fixed points is closed and is open.
Yes,
okay, so it's everything. So this is injective. Okay, so you write these inequalities and you apply it for the maximal compact group. You know its dimension because it's the orthogonal group in R variables. And you get the inequality you want.
Okay.
Okay.
Thank you.
Thank you.